Okay, so in this reaction, we're going to go over the basic directions of just how to balance and how to identify the different types of reactions that we have. So this is like the lowest level, simplest explanation of just the mechanics of how to balance. And then I'll do a second video that goes into a little bit more of how balancing and nomenclature intersect. And then an additional video about how to predict products when you're only given the reactants. So for the first one here, we're just going to talk about the mechanics of balancing, some steps that you can always make sure that you follow to make sure you're balancing correctly, and then how to identify our reactions. So the first thing we're going to look at are our different types of reactions. So there's 5 types of chemical reactions, and the first one we're going to look at is synthesis. So the easiest way to look at synthesis, this is just 2 things coming together to make a new compound. So it could be 2 single elements like A and B coming together to make AB, or it could be 2 compounds coming to make one larger compound. But it's just individual things making one product. So you're going to have 2 or more things on this side, but a single thing as a product. Next one, a single replacement reaction. So a single replacement reaction occurs where I have one element replacing another element in a compound. So the generic form of that would look like A plus BC yields AC plus B. Okay? And so this is A as my single element replacing B in the compound, now bonding with C, forming a new compound, AC, and now B is by itself. So some things to consider here. We know in a properly formed chemical compound that the positive thing comes first and the negative thing comes second. So because of how I did this here, with A before C, that tells me that both A and B are positive ions, and so that means C must be a negative ion. I can also do this by replacing the negative ion, and it would just have to be my single element was also negative to replace the negative and kick that one out by itself. All right, double replacement. So when I have 2 compounds exchange positive ions and form 2 new compounds. So A, B is a compound, C, D is a compound. So in a double replacement reaction, A pairs with D and C pairs with B, and so we end up with AD, positive before negative, plus CB, okay, positive before negative. Decomposition is just like what it sounds like, where something is going to break down into its component parts. So the simple form, AB yields A plus B. It doesn't necessarily have to be 2 parts. It can be 3 parts or 4 parts, but you're going to have one thing on the reactant side and then 2 or more things on the product side. And then our last one is combustion. So combustion is a little different. I'm not going to represent this formula using the ABC symbolism that we used for the first 4. With combustion, I'm going to have some sort of hydrocarbon, so something that contains a certain amount of carbon and a certain amount of hydrogen. So X and Y are just playing the role of our subscripts here. Could be any numbers, but we have some sort of compound that contains hydrogen and carbon. We're going to expose that to oxygen, because combustion is fire, and you have to have oxygen for fire. And then that produces some amount of carbon dioxide and some amount of water every time. So you're going to have varying coefficients in front of the carbon dioxide and the water, and those coefficients are going to have to balance with whatever my subscripts were here. But I will always have these parts in a combustion reaction. No matter what, I'm going to start with something with carbon and hydrogen. I have to have oxygen, otherwise the fire will not burn. And I will always produce some amount of carbon dioxide and some amount of water every time. Okay? All right, so let's go through our general directions of how to balance an equation. So when I look at a skeleton equation, so this assumes that I at least have something written down that I can start with. The first thing that I want to do is check for diatomic elements. Remember that diatomic elements are those elements that when they are not paired with something else, will pair up with another atom of their own type to reach that stability, that octet arrangement. And so we call these the 71st elements. If you look at the periodic table, they start at element number 7, which is nitrogen, and they form the shape of a number 7. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Do you see the 7, the shape? So the 71st elements are those elements there that form the shape of the 7, and then the first element, hydrogen. Anytime those guys are by themselves, we're going to add a subscript of 2, but only when they're alone. If they're paired with anything else, we do not do this. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. Starts at 7, makes a 7, and the number 1. Okay. Once I check my diatomics, I'm going to make a chart to check for balancing. I'm literally just going to take inventory. What do I have on the left? What do I have on the right? Then I'm going to add coefficients where needed. Remember that coefficients are the big numbers that we write in front of our chemical compounds to give us a multiple of that compound. Remember that coefficients get multiplied across whatever formula they're in front of. All right, so let's look at this first one here. So I have Na plus Cl gives me NaCl. So step 1, check for diatomics. Sodium, not a diatomic, but chlorine is. Okay, it's on our list. So I'm going to place a 2 subscript on the chlorine. I would not do it over here because chlorine is not by itself. I'm only going to do it here where chlorine is by itself. So step 1, check for diatomics. Step 2, make a chart. So I'm going to list everything that's on the left-hand side and everything that's on the right-hand side. And I'm going to separate it with that bar. Okay, I'm listing these by the elements because that's what I need to make sure I have the same number of elements. So I have 1 sodium and 2 chlorines. Over here I have 1 sodium and 1 chlorine. So my sodiums obviously are balanced. My chlorines are not. I can place a coefficient where needed to balance. So if I have 2 chlorines and 1 chlorine, I'm going to have to put a 2 in front of the sodium chloride. That's going to change this to 2 and this to 2. Okay, so now my chlorines are balanced, my sodiums are out of whack. So I'm going to then also put a 2 coefficient. Now I'm going to put a 2 coefficient on the sodium, not a subscript. The only time I add subscripts is for the diatomics. Everything else I'm going to add is going to have to be a coefficient. So now I'm balanced. I have the same number of each atom on both sides. And then I'm going to look at this and identify what type of reaction this is. So I have 2 things coming together to make one thing. That is a synthesis reaction. Okay, synthesis reaction. All right, let's do another example. All right, number 2. So again, first thing I'm going to do, check for diatomics. So sodium, no, no, no. Hydrogen by itself, yes, this is a diatomic. So I'm going to place my 2 subscript there. All right, now I need to take inventory of my parts. So I've got sodium, hydrogen, oxygen, sodium, hydrogen, oxygen. Keep them in the same order. It'll just make your life easier. So let's go through and take inventory. So on this side, I have 1 sodium. I have 2 hydrogens. I have 1 oxygen. On this side, 1 sodium, 3 hydrogens, 2 here and 1 there, so a total of 3, and 1 oxygen. Okay, so my sodiums and my oxygens are good. It's my hydrogens that are out of whack. I have an odd-even problem here. The easiest thing to do when I have an odd-even problem is to make the odd side even. Well, when I look at this, notice that I have 2 here and 1 here. So it's really this 1 that's causing this to be odd. But if I put a 2 coefficient in front, that's going to change my sodium to 2, my oxygen to 2, and now I have 2 plus 2 is 4 hydrogen. That's going to make it a lot easier to work with on the other side. So my sodiums, I'm out of whack. I got a 2 and 1, so I can put a 2 here. And then I've got 4 and 2. If I put a 2 here, 2 times 2 makes this 4. and 2 times 1 makes this 2. So 2, 4, and 2, now I'm good and balanced. All right, so what type of reaction is this? I've got sodium by itself, and then look that my sodium ends up in a compound. And now I have hydrogen by itself. Well, let's think about what this is made out of. Remember, H2O is hydrogen, oxygen, hydrogen. If I draw it, could we think of it as a hydrogen and a hydroxide? If you think about it as a hydrogen and a hydroxide, what happens here makes more sense. The sodium replaces one of these hydrogens, pairs with the OH, and now the hydrogen's by itself. So if I'm taking the sodium and replacing the hydrogen, this would be a single replacement reaction. Okay. All right, our next example, NaNO3 yields NaNO2 plus O. So first thing, what do? Check for diatomics. The only thing by itself is oxygen, so I put my 2 subscript there. All right, now I need to take inventory. So what do I have on this side? I have Na, I have N, I have O. On this side, I have Na, N, and O. Okay. 1 Na, 1 N, 3 O. Over here, 1 Na, 1 N, and 2 is 4 O. Okay, so everything's good except for the oxygen, and I have that odd even problem again. So let's make the odd side even. Now this time my 3 is all together, so I'm just going to multiply it by 2, make it 6. So this is going to become 2, this is going to become 2, and 2 times 3 makes that 6. All right, now let's fix it over here. Sodium 2, sodium 1. So I put a 2 here. That's going to make that sodium 2. That's going to make that nitrogen 2. 2 times 2 is 4, plus 2, there's my 6. Okay, so nice and balanced. All right, type of reaction. I have one thing, and it's forming 2 things. So this is one thing breaking up into 2 things. This is decomposition. Okay. Next one. HCl plus KOH yields KCl plus H2O. So no elements by themselves this time, no diatomics, so I don't need to do anything there. So I can skip to going ahead and making my list. So HCl, KO, HCl, K, and O. So 1 H here, 1 H there, that gives me 2. 1 Cl, 1 K, 1 O. Over here, see, 2 H's, 1 Cl, 1 K, 1 O. Look at there, it's balanced. So I don't have to do anything. I don't have to add any coefficients here. I do need to identify what type of reaction this is. So let's see, I've got a compound and a compound, and a compound and a compound. The H was with the Cl, and the K was with the OH, but now the K is with the Cl, and I have H2O, which is really H and an OH. So these guys swapped. So this is a double replacement reaction. Okay, and that leaves us to our last one. So this one is obviously going to be combustion. It's the only one of the 5 we haven't done yet. Combustion problems are notoriously tricky in terms of balancing. So I'm going to take you through a general order of attack when you're dealing with a combustion problem. And sometimes what you're going to find is combustion problems are trial and error. You're going to start one way, you're going to get to what would normally be the end of the balancing and realize I'm not done and I've got to go back and change some things. So don't get freaked out with a combustion problem. We're going to go through a logical way to do it, and then you should be okay. So first thing I need to do, just like any other balancing, check my diatomics. I have oxygen. It's a diatomic. I'm going to put my 2 there. Now I'm going to make my chart. So C, H, and O, C, H, and O. So I've got 2, 6, and 2. And then on this side, you'll find you're always going to have the same answer because you're always going to have carbon dioxide and water. And it's always going to be 1, 2, 3. 1C, 2 H's, and then 2 plus 1 is 3 O's. Okay? When you're doing a combustion problem, you're always going to work from the carbon to the hydrogen, and you're always going to do the oxygen last. Because oxygen, if something's going to throw a monkey wrench in your balancing, it's going to be the oxygen. All right, so let's start at the top and work our way down. I've got 2 carbons, so I'm going to add a 2 coefficient here. So that's going to give me 2 carbons. 2 times 2 is 4, plus 1, now I have 5 on my oxygen. Okay. Hydrogen, I've got 6, and I have a 2 here, so I'm going to have to put a 3 in front of the H to get my 6. 3 times 2 is 6. All right, but I got to look at how that affects the oxygen. So 2 times 2 is 4, plus 3 is 7. So now when I go to balance my oxygen, is anything times 2 a whole number? Obviously, I realize 3.5, but you can't have 3.5 oxygens. Anything a whole number times 2 going to give me 7? Nope. So when you get to this point, when you end up with an odd number of oxygens on the right, this is what you're going to do. You're going to double everything. If I double all my coefficients, then this will end up being, instead of 7, be 14, and then 7 times 2 would give me 14. Okay, so watch how we go through that. So I'm going to put a 2 here. I'm going to change this 2 to a 4, and this 3 to a 6. Now I'm going to go through and update my list. 2 times 2 is 4. 2 times 6 is 12. I'm going to leave the oxygen alone for just a minute. 4 times 1 is 4. And 6 times 2 is 12. Now do my oxygen last. 4 times 2 is 8, plus 6 is 14. And then how do I get 14 on this side? 7 times 2 is 14. So see how we got to the end, realized, uh-oh, we have trouble because we have an odd number and we had to go back. It's okay to do that. So again, this is a combustion problem. And that process is a good plan of attack anytime you're dealing with combustion. Start with the carbon, then do the hydrogen, do the oxygen until last. When you get to the oxygen, if I have an odd number on the right, double everything. That odd will become even, and whatever number you had here that was odd is going to end up being your coefficient here if you've done it right. All right, so in the next video, we're going to go through the nomenclature piece with this, how nomenclature and balancing come together.